Hello students, today we are going to focus on 4 different topics. One, we are going to review what we have done in the last lecture, and the second one is about the correction in the computation of capital GM or the equivalence transconductance. And regarding the third one, we are going to talk about the CS amplifier with current source low. The fourth one is the common source amplifier with source degeneration resistor RS. And so the first topic under the common source amplifier with resistive load, we found that this particular amplifier had a very good swing where we had V out maximum was reaching up to VD, and then the V out minimum was around VOE 1. And the second important point is that the output Q point is basically defined with VDS Q, that is equal to VDD minus ID times RD. Okay. So which means that this Q point is well defined. I'm just trying to emphasize this particular word, well defined, in order to compare the common source amplifier with the other type of loads that we are going to talk next. But having said that, this common source amplifier with resistive load had some drawback in it. One of the major drawback was the gain is not constant when there is a variation in VGSQ. And when there is an attempt, like say for example, whenever we want to increase the gain, there was a major drawback that happened. Assume that I just want to increase the gain because we know that the gain is basically 1 by minus GM times RD for this case, and I just want to increase the gain just by increasing the RD. Now one of the major drawbacks here that I would just point out is the RD, when it varies, it basically controls simultaneously the gain as well as the VDSQ, which means that there is a strong couple of gain and the Q point definition with respect to RD. So if, say for example, if we attempt to increase the RD, then in order to increase the gain, what would happen is the VDSQ would get reduced, and the reduction in this VDSQ would in turn affect the allowable swing at the output. So this was happening just because of the previous statement stating that there is a strong couple between the resistance and the Q point, and the strong coupling between the resistance and the gain. Now we just move on to the second topic, that is a common source amplifier with a diode connected load. Now in this configuration, we had two types of loads that we have discussed. One is using NMOS load, and what we found was the gain had some non-linearity, and this non-linearity basically comes just because of the body effect parameter that comes into the gain expression. And later on, when we try to increase the gain AV, what happened is it leads to a larger sizing of the devices, and in turn this larger sizing would in turn disturbs the speed, or in turn reduces the speed of the circuit. When we looked into the output swing, we found that in this particular case the VO maximum was being limited by a threshold voltage VT, and also the VO minimum was given to be VOE1 of the driving transistor. This is basically VT2. And the third point that I want to emphasize before ratification for the first issue, that is the gain with nonlinearity, I just want to emphasize on the the third point, is that the Q point. We had a VDSQ. Okay, so how does output node VDSQ is basically defined for this structure? So which I hope that we haven't discussed during the class hours. So just want to emphasize the same fact over here. Now I just draw the common source amplifier with a diode connect, or with an NMOS diode connected load, wherein I try to apply gain and I observe the output at this particular node, V out. Now, what is the Q point at this particular output? So this is basically defined by the gate to source of my transistor M2. Now, the Q point at this could be written as VDD minus VGS of 2. So which means that what happens is, like, whenever I just want to increase the Q point at the input, the current would get increased, and the increase in this drain current would obviously modify the gate to source potential across our M2 transistor, and in turn the VDSQ will get altered. So this is my VDSQ of transistor 1, and that would be written as VD minus VGS2. Regarding this first issue that we had earlier, that is the gain had dependence on non-linearity, this could be rectified by replacing this NMOS load with a PMOS load, which we have already discussed in the last class. And I just want to make one of the important remark before I attempt to go for the next type of load, that is the current source load. One of the major remarks that I want to make here is, in both the cases, to increase the gain, we normally went on to increase the load. So either it could be a resistive load RD, so increasing a resistive load would increase the gain, or in the second case, in order to increase the gain AB, we know that the gain expression for a diode connected load could be written as GM1 divided by GM2, and just in order to increase this GM1, we could either play with W by L factor, or the other case is with respect to VOE. But in all other cases, what happens is the swing is getting disturbed. And in the previous case, what we have done is, when we go for increasing the load, the Q point is getting altered. And even here, in this case, whatever I try to do in order to increase the gain, that is either by working around W by L factor or something. So we found that when we work with respect to W by L factor, we found it was W by L of 1 divided by W by L of 2 under the square root, and we also had a different option, that is VOE 2 by VOE 1. So in any of these cases, whenever we try to work around the gain, even in this case the Q point would get modified. So what I really wanted to tell here is there is a strong coupling between the gain and the Q point in both the cases. Now we need a solution for this, like trying to identify a circuit that actually decouples those two things. Now let us look into a circuit where I still want to increase the gain by increasing the load, but that should not in turn disturb the other quantity, that is either the Q point or any of the parameters in the circuit. So the one that strikes us is a circuit which has a larger load, would be a common source amplifier with a current source. We know that a current source in general will have an infinite impedance, so let us try to build a circuit out and then see how the gain would then define right now. Now what happens is, like, I have a driving device M1 through which I try to define my input, and I take the output from the drain terminal of my M1. So before I just label this, I'm just going to have a coupling capacitor, and I'm just going to attach a residual load to it. Now this gain could be written as minus GM1 times that of the load resistance RL. So thus the gain at a low frequency could be written, and whenever we just want to increase the gain, we can really work upon this RL in order to increase the gain. So increasing this RL will not affect the GM in this particular case because of this very, very huge coupling capacitor between them. So in other words, using a constant current source biasing, we can decouple the gain and the bias so that each can be adjusted independently. So I will write it again. So using this kind of configuration, it is actually possible for us to decouple the gain and the Q point so that each of these parameters could be adjusted later on independently. Now let us try to implement this constant current source with a CMOS device. This could be implemented with a simple current mirror structure where I assume that some I reference is running around the circuit, and I am using that and I'm just passing through the simple current mirror with a diode connected M3 and M2. As we know that this simple current mirror would actually copy the I reference and produces an output ID2, and depending on the ratio between M3 and M2, the factor of ID2 would be either increased in multiples of I reference or could be reduced in multiples of I reference. So for time being, let us assume that both the W by L of M3 and M2 are same, and this node is going to get connected to our driving device. So according to this section, we know that the current ID is basically can be defined as a function of VGS. So based on this, I just want to measure what could be my VSG3. So since the current that is flowing through M3 is basically I reference, I can write VSG3. That is, so I write this VSG just because it's a PMOS device where the source is at higher potential than compared to our gate, and this could be written as an inverse function of our I. So once I capture this VGS3, I can transfer this to the gate to source potential of my PMOS device. So bring this VSG3 to VSG2 and then apply the function so that upon this VSG2 in order to derive the value of ID2. So this is what we do through this simple current mirror, and this is how the ID2 is basically being generated. Now for this case, let us try to draw ID versus VSG graph. This is a PMOS and using a reverse notation over here. So this is my source to drain potential VSG2 versus the current ID2. Since the value of VSG2 is basically fixed, there will be a single current that will be defined, and that I will mark it, and this is for a single value of VSG2. Now we know the output characteristic graph for our transistor M1, which I will draw it in the next page. So which is basically ID1 versus VDS1, and we know when our input is getting varied over a larger variation, so what happens is we will have a set of lines. So these lines are basically for different values of VGS that I apply across the input of my M1 transistor. In order to discuss a large signal analysis, what we wanted is to merge both these graphs and find the load line out of this particular graph. So now what I'm going to do is to just copy the previous graph, and then I'm just going to put it over the next page, and let us see whether we can draw a load line out of it. So before I really start drawing the load line for this configuration, what I really wanted to do is, like here the definition is basically putting drain to source of transistor M1, whereas here the graph has an x-axis which is defined the source to drain potential with respect to M2 transistor. Now when I really map those two graphs, I have to make sure that the terminology that I use should basically map. Now in order to make things clear, I just take a part of this particular circuit and then put it over to the next page. So what I really wanted to do is, whatever the definition that I have here has to be defined. That is, the definition that I have between the source and the drain is nothing but VSG2. So this notation has to be transferred in terms of VDS1. So this is our first step in order to merge both these graphs. So how I can define my VDS1 in terms of VDS2 is basically, we know that the potential that I have over here is the summation of drain to source of M2 transistor plus the drain to source of M1 transistor. And what I really wanted is this notation, which I can do a simple arithmetic. Now based on this expression, we can really start merging. Now before I start merging, I just want to replicate this VDS1 and then ID2. So anyhow, the current through both the transistors would be same, so I can just equate this xk to be the same. So both my ID1 and ID2 is going to be the same. But what changes that matters here is my VSG2 and VDS1 definitions. Now, so this is the point where my VSG2 is basically 0. I just substitute that value. I just try to use a different color. So here my value is 0, and that when I substitute over here, my VDS1 would actually map to a value which is equal to VDD. So I mark the same point over here at VDD. And we also know that the point of separation between my linear and the saturation could be defined as VSG2 minus VT2. So, or in short, I can state it as VOE2. Now, this point, I have to refer back over to the scale of my x-axis in this new graph. So that will be done again by substituting those values. And this leads to the new definition of my VDS1 over here. So this point has to be mapped over here. So from VDS and VOE2, and that would point to somewhere over here. So this is the point where I simply mark this point over here. Now, following the same kind of notation, what happens is like this is the point where my VDS2 has reached my VDD. So when I substitute over here, over to this expression, that would lead to the point somewhere closer to a 0 value. Now, redrawing the same graph would basically map something like this. So this entire graph has been offsetted by a value of negative VDD. Now, over this graph, this particular structure has been mapped. I'm just going to try to copy this. Hopefully it should work to some extent. So now what happens is like I have to look for regions where both my M1 and M2 transistors are in saturation. So again, we get able to see that there is an intersection between those two graphs at these locations, which I can mark it through this yellow dots or yellow cross marks. Now clearly it indicates that it is only after this particular region my M1 transistor get into saturation, and clearly for my M2 it is after this particular point where my M2 enters into saturation region. So what happens is basically the region of operation is defined at the lower end by VOE1, and the region of operation at the upper end is defined by VDD minus VOE2. So that in turn translates to our minimum output swing, and this would be our maximum output swing. So I would state that in the next page. For this configuration, the VO max is basically defined as VDD minus VOV2, and my VOut minimum is defined as VOV1. So that completes the large signal analysis of our common source amplifier with a current source load. Having said that, we haven't yet calculated the gain of this particular structure. So I'm just going to again copy this structure to the next page, talk about the gain expression. As we know that the gain expression could be written as the GM times the output impedance. In this case, to compute this with the GM, it is pretty easy. As we have done already, capital GM would basically relies on the value of M1, and that leads to just GM1. And regarding the output impedance, just look across the output terminal, and when I look up, I'm looking into the drain terminal of my, and the drain would be equivalent to RO2. And again, when I look down from standing from my output node, I'll be again looking into the drain terminal of my M1 transistor, and that would sense our impedance of RO1. And these two impedances would generally go in parallel, and my output impedance could be defined as RO2 in parallel with RO1. And that's the small signal gain in order to extract the information from this graph and then put it onto our Vout versus V graph. So whenever there is a variation across my input, we will be looking at what happens to the output at the other end. Clearly, when the input is at 0, the output was at VD. So I'm just going to map that particular point over here, and then I equate that into VDD. Now, before the output reaches to this particular point or this particular intersect, the input is basically being increased over quite a distance. Okay? So, what I can state is my input is at VT, and beyond VT, I just go here, and then after that I intersect to this least point over here. So in general, I can mark this as the exact spot where my transistor EM2 gets into the saturation region. Until this point, my transistor EM1 is basically in cutoff. And immediately after cutoff, my M1 was first entered into the saturation region, but my M2 transistor was still in the linear region. That is, I'm talking about this particular region. Now, once I reach to this particular spot where the output voltage could be defined as VDD minus VOV2, when I reach to that point, then this is the place where I have both my M1 and as well as my M2 that are in saturation region. Now, this relationship holds till I reach to a particular, this is where my output will be, and for that the corresponding input will be there, and which I'm just going to mark it as VI. Let us assume it is a V or something else. So some different value. And this VIB in general defines my VOV. So some reaches value which I label it as VIB, and so that my VDS1 is nothing but it has to be equal to VOV1, and that is defined in terms of VGS minus VT, where right now this VGS is being mapped to VIB minus VT1. That's it. Correct? And after that, what happens is my transistor EM1 gets into linear segment, and whereas my EM2 transistor stays inside the saturation region after that. Okay. So this is the spot where I really work on when I try to bias both the transistor M1 and M2 into the saturation region. Now regarding the demerit, okay, let me put a question over here. What is the output bias voltage for this circuit that is common source amplifier with a current source load? So I just redraw the structure quickly, and in the meanwhile you can just think what might be my VDSQ or VOutQ at this particular point. So any idea that you have generated? As you guess here, so the output can go all the way up to a point like this is my VDD, and there should be a drop of VOV2 so that my transistor would stay in the saturation region, and when I go towards the lowest thing, and this is the ground level that I have, and I need the voltage drop between the drain and the source, which is at least a minimum of VOV1, so that my transistor M1 stays inside the saturation region. But the point here is, what is the baseline that is defined? Now, this particular circuit that I can state it as a drawback doesn't have the output bias voltage that is well defined. So, and this basically happens as a result of decoupling. So, where in the previous case we had a strong couple between the load resistance and the gain and the Q point, whereas in this case when we try to decouple, and this is what we end up. But I mean, this could be fixed by having some feedback loop so that this output node could be fixed, or the Q point at this particular node could be fixed to a known value. Regarding this fixture, or regarding the feedback through which we try to define a well-defined value to this particular node, will be discussed later on while we discuss differential amplifier with the common mode feedback. So for currently, we just assume that this particular circuit lacks a well-defined output node or output bias voltage here. Now regarding the other end, let us assume I just want to reduce the VOE value so that the output maximum can all the way go almost closer to the value of VDD. So this could be done just by increasing the value of W2. But so increasing this value of W2 would in general, for a given current, would reduces the requirement of VOE2. Now the next thing is I just want to check about the gain expression again and just see if there is any possibility of increasing the gain or to this particular part of the circuit. So I'm just rewriting this expression of the gain. Now let us try to work around the gain individually across M1 and M2 transistor and then try to see how I can improve the gain for this particular circuit where there is a requirement of the gain of large value. So now that we will look across transistor M1 and M2 separately and just see how to improve the gain. Now we know that the way by which we can increase the gain is by increasing the value of RO1, and in general the RO1 or before I start stating about RO1, I try to emphasize on lambda. We know that the lambda is basically inversely proportional to the value of L, and in turn that leads to the output impedance, which we know that it is proportional to L by ID. So due to this particular factor, there is, in order to increase the value of RO, I have to increase the value of ID. So let us try to do that across our M1 transistor and then see what happens in the other end. So when we try to increase the value of L1 by some factor, even the value of W1 has to be increased by the same proportion. And this has to be done just because we know that the VOV1 is basically related to the expression which is 1 upon square root of W by L of 1. So if L1 alone is being scaled up, what happens is the VOV1 would basically shoots up, and in general we are trying to reduce the output swing. So that's the reason why to improve the gain, or in order to improve the value of R0, we have to scale both the L1 and the width W1 by the same proportion. Else we'll end up with a larger value of VO1, and that in turn would affect the output swing. And I can even state there is one more reason where the L1 W1 has to be increased by the same proportion, for which I will take my GM1. So we know that this gain is also related to our GM1, and this GM1 is basically proportional to the square root of W by L of 1. So what happens when we try to increase the value of L1 alone without changing the value of width? So again, the GM would start scaling down. So that's the reason why we have to increase both L1 and W1 by the same proportion. If it's not so, we'll end up with increase in VOE and a reduction in my GM1. The same argument could be applied even for RO2 as well. Whereas in the case of RO2, it is only the factor VOE2 that comes into picture. So here again, I have to work both with L2 and W2 in order to maintain the same value of VOE for a given current. That completes the discussion of common source amplifier with a current source load. So the next topic would be a common source amplifier with a source degeneration resistance. So first, I'll just quickly make the circuit before we really start analyzing the circuit, where the gate is applied with an input and the output is basically taken from the drain terminal of this M1 transistor. We know that the gain could be defined as the transconductance of the circuit into the R out the circuit, the output impedance of the circuit. Now, in the last video that I have discussed about the computation of GM, there was a bit of correction that I have to make, and that is what I have stated earlier, that the second focus is on the calculation of capital GM. So first I will write down the steps that we have to follow when we try to compute the capital GM. So which I will state it here. So the first step is to draw the small signal model for the circuit, and the second one is to freeze the circuit and then short the output node to ground in order to measure our I out. And later on we know that just by having I out, or just by using the expression I out by PU, we can get the value of capital GM. So we'll just follow these steps in order to compute the capital GM, and then see how the results are different from the previously calculated result towards basically a wrong result. So now let me do the first step. That is step number 1, is to draw the small signal model. So I have my Vin, and this Vin is connected to the gate, and the source terminal is basically not grounded in this case, which is being connected to the source resistance RS, and there is a drain terminal, and the drain terminal has a resistance RD, and it's also being connected to the node VO. And we know for this polarity there will be a current that will be flowing from drain to source, whose value is GM times VGS. And then whenever there is a channel length impact, we'll have a resistance R0, and then there is again a current source, and this current source value would be GMB dBs. And this current source comes into picture whenever there is a potential difference between the source and the body. So in this case, the body is at the ground potential, whereas the source is not at the ground potential. So this is the first step, step number 1. And now, step number 2, I stated that I have to freeze the circuit, which means that the circuit should not be changed once you complete the small signal model. So which means that I can directly short this particular node to the ground and try to measure the output current. And in the previous case, I did a mistake stating that since the resistance R0 is attached between the source node and the ground, this could be pulled down, or this resistance could be pulled down and placed in parallel with R0. But that is wrong, because once the circuit is drawn, the circuit is freeze. You don't have any authority to change the circuit after that. So I'm not going to put that resistance in parallel with RS. The only thing is I'm just going to use the circuit as it is. Now this current I out would start flowing, and it tries to find a path here. But since the resistance, or since the potential across the resistance RD is same in both the ends of its terminal, the current will not flow through this resistance RD. So the other way that it can flow is through the GMB VBS, and through R0, and through GM VGS. So it flows through R0 just because the one end is at a different potential, which is nothing but the ground, whereas the other end of my R0 is not connected to the ground. So there is a potential difference basically. Now let us try to define this I out to be summation of two currents. One is GM VGS, and the second one is GMB VBS. The third one is the current through the resistance R0, which could be written as the potential difference at the drain minus the potential at the source divided by the resistance R0, and that leads to the current. Now let us try to redefine this VGS and VBS in terms of the known parameter. Now this VGS could be written as VG minus VS, and since the gate is connected to our Vin, we can rewrite the VG with Vin, and the source is basically connected to a resistance, and the current that flows and the potential across the source is basically computed once the current through the resistance is known. So we know that all of these currents that are branching out in all the three branches would basically get merged over here, and the current that we would get here would be the same I out. Now, so for that, the source voltage or Vs could be defined as I out times Rs here. And again, I'm just going to redefine the VBS as the potential at VB minus the potential at the source. We know that the potential at the body is basically ground, and that could be mapped to 0. And then the potential, as we know, it is nothing but I out into Rs. And the Vs could be written as just I out times Rs. So mapping all of these expressions onto this current equation would lead us to write, shifting this part of this expression towards the left hand side, and then mapping would lead us to, and now I'm just going to do a simple arithmetic. That is, I'm just going to define this Gm, which is nothing but I out by Vn, and that could be readily extracted by shifting this Vn towards the left hand side, and that leads to an expression which is defined as Gm R0. So cross multiplying this R0 over those two places and then shifting this denominator to the numerator would lead us to this expression, which is R0 plus Rs plus Gm prime Rs R0. Now this is the expression of our capital Gm for common source amplifier with source degeneration resistance. Now the second part, in order to compute the gain, is to compute the output impedance. So it's nothing but our Rout. So again, let me try to put back the circuit here. So this time I'm not going to draw any small signal model. What I will really do is, whatever we have learned, we'll try to utilize that to quickly extract the Rout expression. So starting from the output node, when I look up, the resistance that I see is just RD, and when I look down, the resistance that I would see, I write it as Rx, and that could be defined as what? We know whenever there is a source resistance, and when this resistance is looked from the drain terminal of M1, this would get magnified by quantity which could be defined as Gm prime of transfer 1 times RO1 times the Rs, and this is an approximate value. And if I try to expand this terms, that would lead to something like this. So which means that the Rout is defined as Rd in parallel with the whole expression, which I label here as Rx for simplicity. Now I'm just going to write the gain, which is defined as capital Gm times Rout. And when I look into this Gm expression, the quantity that I have all the way down to the denominator is nothing but the same Rx value that we have defined over here. So just rewriting this expression in terms of Rx so that it would help us to look into the expression betterly. So I'm just trying to write the Gm in terms of Gm R0 divided by capital Rx, and this Rout is very simple. It's nothing but the parallel combination, and I'm just going to expand this parallel combination as Rd times Rx divided by Rd plus Rx. Cancelling out the kind of common terms, Rx would lead to the gain expression, which is Gm R0 and then Rd at the top, and over to the bottom it is Rd plus the total impedance of Rx, so which I am writing here just to make sure that we are clear with what I have done. Now let us try to understand a bit more, since we just want to compare how good this common source amplifier with source degeneration resistance when compared to all the previous common source amplifiers. So in order to make this understanding better, I try to rewrite this expression, gain expression, which is Gm R0 Rd divided by Rx. Okay, so this time I just try to expand this Rx so that I assume that you remember it as well. So which is nothing but Gm prime Ro Rs, then R0 plus Rs, and then that has to be added with the Rd term. And this is the total gain, and out of that I redefine my Gm, that is Gm is nothing but Gm R0 and then all the terms except the Rd term. So which would be Gm prime Ro Rs R0 and then Rs. Okay. So this entire term will get fit into my capital G. Let us look into the case where what happens when we have lambda equal to 0 and then gamma equal to 0. So what happens to this capital Gm in that particular case? So I just want to make a transformation from this definition of capital Gm to the simplified expression by adopting lambda equal to 0 and gamma equal to 0. So to make sure that you understand better, I'm just going to take this term out and then I try to cancel out the term which are at the bottom. So that would lead to something like this. That is by gamma. So now when lambda is set to be equal to 0, what happens to the value of R0? The R0 goes to infinity. And that when I substitute over here, it is just this particular term that goes to 0, and that simplifies the expression to Gm divided by Gm prime. So this time I'm just going to assume that the lambda equal to 0, which means that this Gm prime is mapped onto just Gm itself. So I'm just rewriting here by adopting that the lambda value, that the gamma value is taken into account. And then that leads to a very simple expression. Now let us look into the R0 expression. As we know that the R0 is nothing but Rd in parallel with all this Gm, R0, Rs, R0 and Rs. So again, when I adopt lambda that is equal to 0, what happens to this entire combo? So this entire thing would lead to an infinity. So anything that we have in parallel with an infinite impedance would lead to the smallest resistance, that is nothing but the Rd term. So these are the terms that we would end up when we assume that the lambda and the gamma are equal to 0. So let us look back and see what exactly those simplification tells us or gives an intuition behind that. Let me draw the Gm versus Vn, and for the first case I'm just going to adopt a common source amplifier without source degeneration resistance. So I'm just going to use the orange color to do it. As you know, like when till our Vn is less than Vt, there is no current, and because of that the Gm is basically 0. But beyond Vt, what happens is, we know that the Gm of a CS amplifier without source resistance Rs is nothing but Gm itself. And we know the definition is given by K dash W by L, and it's basically directly proportional to VGS minus Vt. And because of this relation, that there is a direct proportionality between Gm and VGS, it leads to a line like this. So let us see what happens the moment we have a resistance Rs, and what happens to the graph. So the major thing is, like, we have to take back the previous expression, that is our capital Gm, when lambda equal to 0 and gamma equal to 0 was defined as Gm divided by 1 plus Gm times Rs. Now I'm just going to do a simplification by taking out this Gm out, and that would lead to 1 upon 1 Gm plus Rs. Now, as you know, during till Vt, there is no current, and the value of Gm would be equal to 0. And when this particular term is equal to 0, then this particular term would become infinity, and the entire capital Gm would rather goes to 0 again. So it is almost identical to what we have got earlier. So till this particular point, Vt of our input. But what happens after this? And what could be the maximum? As you know, that as V increases, the Gm would start increasing. And in general, this particular parameter would basically goes down and down and down. And that would lead us, it goes like this, and at a particular point, this 1 upon Gm keeps on reducing. As I increase the value of input V, the Gm keeps on increasing, and 1 upon Gm keeps on reducing. At a particular point where when the gain is so high, this value is almost closer to the value of 0, and the entire capital Gm could be approximated to just 1 by Rs. And that would be the maximum value that we can get, and that could be mapped over here. And the graph could be drawn something like this. Clearly, this particular circuit shows us that after a particular value of Vn, the Gm of the circuit is almost constant in this particular phase. Whereas in the previous case, once our V crosses Vt, any change that you make at the Q point or any change that you make at the input would directly in turn affects the Gm. Okay? The more the Vn that you apply, the more the Gm that you would get. But here it is not so. So once you cross a particular value, the Gm is almost constant over here. Now let us look for the currents. So in order to discuss about the current, first let me draw the current that we normally get for a circuit without source degeneration resistance, and then we'll talk what happens to the current when there is a source degeneration resistance. So for which I just redraw the circuit, and then let me try to map ID versus V. So again, till Vt, H, there is no current, and I'm just doing with the color of yellow. So the yellow denotes the current with respect to CS amplifier without source degeneration resistance. It is something like this. I have only RD and there is no source degeneration resistance. This is for this particular circuit, how the current would react. As you know, it's a very simple graph. Once it crosses Vt, you would get a kind of current which goes like this. Now let us try to draw the ID graph with respect to this particular circuit where we have a source degeneration resistance. Now what happens is initially there would be a kind of slope, a non-linear slope, and after that the current would become almost linear. And the slope of this linear line would be equal to 1 by Rs. So why that happens? As you know, like once the value of V keeps on increasing, the potential across this would almost stays constant, and whatever I increase beyond a particular value would actually fall only across our Rs. And the more the V that I apply is only a small change that happens across the gate to source, but there is a huge change that happens across the resistance Rs. And the current that flows, the ID current, could be redefined as Vs by Rs. And this could be approximated, since because once the drop across this is very small, the source potential could be written as the direct read that is being applied over here, and that is being divided by us. What I really wanted to say here is the drop across this gate to source is very minimal, since because there is a feedback that is formed between the output and the input through the resistance Rs, and since because there is a very small drop across this gate to source, the whatever the potential that I have is almost identical to the source potential. So barely some millivolt difference would be the case. So that's the reason why I could able to approximate the value of Vs to be almost equal to Vn, and that is the one that I have written over here. And this is the reason why the drain current makes this kind of relation then compared to this kind of relation. So that's the reason why we have this kind of relation. Hope I have given enough intuition behind this circuit, and in the next video we'll be discussing about common drain and common gate. Hopefully